What happens when a wave hits a wall? By the end of the video, you'll understand these two things. One, what happens when waves reflect or transmit at boundaries, and you'll also learn what those words mean. And two, how wave interference works. So destructive interference, constructive interference, and partial interference. Now, when a wave hits something or gets blocked, it reacts in one of three ways. The first two ways it reacts depends on whether or not it's a fixed end wave or a loose or free end wave. Let's start with a fixed end wave. So let's say you have a rope and you tie it to a fence pole. It's fixed at the end. Okay, and you give it a little flick and the wave travels through like that. It's moving this way, this shape. When it reaches the end, it's a fixed end. It doesn't have space to move, right? This point is fixed. The end point, it stays in one spot. So it punches back in a way. Because of Newton's third law, it sends back an equal and opposite reaction. And what happens to the wave is it inverts, and then it keeps traveling back. So it bounces off and then flips 180. That's what happens when it's a fixed end. How about for a free end wave? Imagine you have a metal pole and you have a super light ring attached to this pole that slides up and down with no friction. You have a rope attached to it. So if you move the rope up and down, the ring also moves up and down. And you give this rope a flick, and it sends a wave traveling toward the pole. It moves forward. What happens when it hits the end? It's a free end. There's no opposing force. There's nothing being sent back. There's no force that inverts it. So it simply bounces back upright. It travels back. No inversion. The third way a wave can react when it hits something. Well, it's not when a wave hits a wall. I'll show you. Imagine a rope that's tied to a second rope. So you have a light rope and you have a heavy rope. We'll represent heavy with red, okay? Red means heavy. And your light side rope is moving toward the heavy side. What happens at this collision point? What happens to the wave? What does it look like? So it's flying through along the rope, the shape. And when it hits, what happens is that the light side rope, some of it's reflected back and inverted, just like a fixed end. But some of it's also transmitted to the heavy side. Continues moving forward. You can imagine it like they bounce off each other. Of course, this side inverts. And depending on the difference in mass, most of the wave is going to come back, and only a small bit gets transmitted to the heavy rope. What if instead it was flipped? So we went from a heavy rope to a light rope. This is interesting. So a heavy wave is traveling toward the light rope. What happens is that some of the heavy rope, small amount, is sent back. Just like the free end rope. It's sent back without inverting. It's still upright. And a lot of the energy is transmitted to the light side and continues moving forward there. Here's something important. Wave speed and wavelengths change. So when a wave enters a different medium, for example, a sound wave moving from air into water, the speed changes, but the frequency stays the same. So how often it vibrates every second. That's set initially by the source of the wave. So if the speed changes but the frequency doesn't, then what is changing? It's the wavelength. It's the distance between crests. So if you look at the speed formula for waves, you can rearrange for wavelength and you get wavelength equals velocity over frequency. So it's connected. If the speed drops, wavelength is shorter. And this might happen, for example, in a heavier rope or a denser medium. Take a look at this diagram. You have an incident ray, or let's say this is sunlight or something. And then when it reflects, goes up like that, bounces off the ground. These angles from this line, by the way, it's called the normal. The angles are equal. What are rays? What are these lines? These aren't waves. There's something called wave fronts, and it's the crest, and it's shown spreading out like this. And the rays are like the vectors. They show the direction that's moving in, and they're always perpendicular to the wave fronts. This stuff applies to things like echoing sound, light bouncing off glass, or water bouncing off the walls of a pool. Now, how about the math? We haven't looked at any math, have we? If two waves hit each other, do they pass through, do they cancel out, or do they add? The answer, yes, all of the above. It's called interference. It's when two waves pass the same space at the same time. When two or more waves meet, the resulting displacement is the sum of the individual displacements, so it's just addition. And there's a few types of interference, and we'll go through all of them one by one. The first type is constructive interference. It's when the two crests and the two troughs line up. What does that mean? It means when the highest points and the lowest points match up. See, they're at the same height. So if this wave's coming this way, this wave's coming this way. Since they line up and the resultant displacement is the sum of the individual displacements, then you just have to add them up like that. If you have two upward pulses that look like this, and they're moving toward each other, let's say like on the same rope, when they collide, here's what happens. They turn into one bigger pulse because you add up the displacements. And then they bounce off and happily travel out in the opposite directions again. Try and visualize this motion in your head. Okay, they're moving toward each other, collide, and then split back away from each other. So it's either when two crests line up or two troughs line up. The second type is called destructive interference. And destructive interference, it's when a crest and a trough collide. So for example, you have an upward pulse coming this way, a downward pulse coming this way. What happens when they collide? The displacements cancel. You don't add them, you minus them because they're opposite directions. And let's say these are of the exact same height. The displacements will equal a net zero. What does that look like? So at the collision point, they're floating toward each other. It turns into a flat line for a very brief moment. So try and imagine this, they slide into each other and it turns into a flat line. Even if it's flat, kinetic energy is still present because 1 instant later, they swapped position like that. So they move through each other and at the collision point, their displacements add to a net zero. The last type of interference is partial interference, and it's when waves are not perfectly aligned. So the amplitude are different. The heights of the crest and the troughs are bigger and smaller. And of course, it depends on the relative amplitude and wave pulse properties. In real life, at concerts, there's speaker arrays that use phase alignment for control. And noise-cancelling headphones, how do they work? The sound waves coming in from outside, they invert them to cancel the background noise. This makes studying 10 times easier. Go download the free cheat sheet in the description and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.